So in 7.1, we sort of got our feet wet with the idea of using trig identities to evaluate, simplify, and prove trig identities. And the only identity that we pretty much used was the Pythagorean identities. The rest of the unit is just going to be slowly introducing you to more and more different identities and relationships that exist in the world of trig. 7.2, as you can see, will be all about these things called the sum and difference identities. And by the end of the lesson, we should be able to use these identities, which involve adding, subtracting angles inside of a trig function, to do the same things we did in 7.1, to evaluate, to simplify, and to prove. So right off the bat, here are the sums and difference formulas for the various trig functions, sines, cosines, and tangents. So these are sort of the rules or the patterns that tell us what to do if, instead of taking a simple sine of an angle, you're taking a sine of an addition problem. What if you're taking a sine of two angles added together, or taking a sine of two angles subtracting? Same thing with cosines and tangents, right? Now, I'm not going to include in this video where it comes from, for two reasons. Number one, I'm pretty sure 99.9999% of you aren't really interested in where it comes from. But the other reason is it would probably bloat this video. If you are truly interested in where it comes from, as always, I'm more than happy to show you in class. Please just ask me in class and I'll gladly show it. So if you want to pause the video for now so you can copy these patterns in your notes, go ahead and do so. I mean, these aren't anything special. You can find them in any textbook, or if you Google trig sums and difference formulas, they'll pop up. I use the variables alpha and beta. You can use whatever variables you want. You can use x's and y's, a's and b's, what have you. So why are sums and difference formulas important? Well, you know how back in Unit 5 I said that when it comes to trig, most people nowadays turn to a calculator unless it was one of those, quote, special unit circle angles, like 30 degrees, 115 degrees, 210 degrees, so on and so forth. Well, you ever stop and wonder, how did people back in the day do trig when calculators weren't invented? How did they do things like, cosine of 75 degrees, or in the radian system, say like a cosine of, pi 12 degrees? Well, if they knew that these special unit circle angles existed, and they realized that, if we combine special angles, either through adding or subtracting, we should be able to find the exact values just as we did with the special unit circle angles. How do we do that? Well, they do that with these formulas here. And using them is very simple. You just basically follow the rules, follow the patterns. So let's take a look at an example here. What are some things I expect you guys to be able to do? Well, I expect you guys to find the exact values to evaluate, right? Suppose I ask you to find the exact value of, cosine of 75 degrees. Now, 75 degrees is not one of our special unit circle angles. So the first thing I do is I ask myself, what are the special unit circle angles, right? So the special unit circle angles are the 30 degrees, 45 degrees, and 60 degrees, right? At least in the first quadrant. If I had to do something in the second, third, fourth quadrant, I'd just use as reference angles. So then this is what you have to ask yourself. Okay, how can I get 75 degrees from 30 degrees, 45 degrees, 60 degrees, using adding or subtracting, right? So it's sort of like a puzzle. You have these cards here, and you need to arrange any or all of these cards so you end up with 75. Now, I hope it's not, a hard thing to think about, but I hope everyone understands that 75 degrees is the same thing as 30 degrees plus 45 degrees. So now we can answer the question. Cosine of 75 degrees is cosine of 30 degrees plus 45 degrees. That is a true statement. And notice we do have a pattern for that. We do have a pattern for cosine of something plus something else, right? So that's all. That's it. You're done, basically. You just have to remember that Whatever your first angle is your alpha, and whatever your second angle is your beta. So this is going to be my alpha, this is going to be my beta. So all you're going to do, again, I'm not doing anything crazy or special. I'm just going to go ahead and follow the pattern, right? So instead of scrolling back and forth, I'm going to assume you have the pattern in front of you. So hopefully you know where I'm going with this. So according to the pattern, it's going to be the cosine of the first angle, cosine of the second angle, minus sine of the first angle, sine of the second angle. And since these are special unit circle angles, I expect you guys to be able to find the exact value. So we should know that cosine of 30 degrees is radical 3 over 2. Cosine of 45 degrees is radical 2 over 2. It's actually 1 over radical 2, but I went ahead and rationalized it. Sine of 30 degrees is 1/2. Sine of 45 degrees is radical 2 over 2. So that gives us rad 6 over 2 minus rad 2 over 2. They have a common denominator, so just squish it together. Actually 4, sorry, I can't multiply. 2 times 2 is 4. And since they have the common denominator, I expect you to squish it all as one fraction. So that is the exact value of cosine of 75 degrees. So it's a pretty neat idea if you really think about what we've accomplished here. We found the exact value, no decimals, no approximation, the precise value of a non-unit circle angle. Pretty cool. Of course, I expect you guys to be proficient in degrees and radians. So if I ask you to do the same thing, find the exact value of, let's stick with cosine, say pi 12ths. You run through the same logic, right? So you ask yourself, what are the special angles? The special angles are pi thirds, pi fourths, pi sixths. Now, when it comes to radians, I try to match what the denominator is. So sometimes it's hard to think in terms of pi thirds, pi fourths, pi sixths. Now, because I want cosine of pi 12ths, I'm going to think in terms of pi 12ths. And I know that pi thirds is 4 pi 12ths, pi fourths is 3 pi 12ths, and pi 6 is 2 pi 12ths. And your job is to figure out, okay, how can I use these angles, either adding or subtracting, to get to 1 pi 12ths? And I hope you guys can see here that we have lots of options. I could do 4 pi 12ths minus 3 pi 12ths, or I could do 3 pi 12ths minus 2 pi 12ths. The cool thing is, you'll get the same result in the end. It really doesn't matter. For the sake of notes, I'm going to use these two here. I don't know why, because it's closer to me. That's a stupid reason, but that's the reason why I'm going to give you. So knowing, according to my scratch work here, that pi 12ths is the same thing as, what is it? Is it this guy minus this guy? 3 pi 12ths minus 2 pi 12ths. So it's going to be pi fourths minus pi 6, because that's what the 3 pi 12ths and the 2 pi 12ths was. And then again, all I'm going to do is follow the formula. So if you go up to the subtraction formula for cosine, just go ahead and follow this formula. The first angle is alpha, the second angle is beta. I'm going to use the terms first guy, second guy. So according to the pattern, this equals the cosine of the first guy times cosine of the second guy plus sine of the first guy times sine of the second guy. And then you just evaluate. Since these are special unit circle angles, I expect you to know what to do. So this is going to be cosine of pi fourths is radical 2 over 2. Cosine of pi 6 is radical 3 over 2. Sine of pi fourths is radical 2 over 2. Sine of pi 6 is a half. So it's very similar to what we did before. So this is rad 6 over 4 plus rad 2 over 4. Since they have the same denominator, you can squish them together as one fraction, right? So that's a pretty neat thing with the sums and difference formulas. Again, we were able to find the precise, no decimals, no approximations, precise value of a non-unicircle angle. I'm going to expect you guys to be able to go forwards and backwards with this. It's nice to be able to use it, but it's even more important, especially in calculus, to identify when it comes about. So you might see problems like this. Find the exact value of sine of 20 degrees, cosine of 40 degrees, plus cosine of 20 degrees, sine of 40 degrees. So when you look at this, you're probably going, we can't do this. 20 degrees, 40 degrees is not a special, those angles are not special. But you should recognize that this whole expression, it's very suspicious. The structure is very, there's sort of a pattern going on. Notice how they use the same angles. They use 20 degrees and 40 degrees. So using informal terminology, what we have here is sine of one angle, first angle, cosine of the second angle, cosine of the first angle, sine of the second angle. Hey, that seems like the pattern for our sums and difference formulas. So all you need to do is look at your identities and see which one follows that pattern. Sine of the first, cosine of the second, plus cosine of the first, sine of the second. So if you look at your lists, we're looking for that pattern there. Sine of the first, cosine of the second, plus cosine of the first, sine of the second. I hope it doesn't take a lot of searching, but that's precisely the sign of a sum formula. Sine of the first angle, cosine of the second angle, plus cosine of the first angle, sine of the second angle. That's exactly what our problem is. So I know that this example here is going to equal sine of the first angle plus the second angle. And when we can just simply see that it's first angle plus second angle, which is sine of 60 degrees, which is a special unit circle angle, and I hope we all know that sine of 60 degrees is radical 3/2. So that's pretty neat, right? This giant ugly mess, we were able to compute without a calculator that whole guy equals radical 3/2. So that's just going to be something that I'm going to expect you guys to be able to do, is use these sums and difference formulas to evaluate, right? To find the exact value without a calculator. But of course, the bulk of this unit, what is the whole point of learning these identities, is to manipulate trigonometric expressions, is to rewrite trigonometric expressions, is to use to apply algebra to trig. And one context that we do that is with proving, with verifying. So this would be a stereotypical problem you'll see. It's just like 7.1, except you have more toys to play with. So suppose I ask you to verify 1 plus tangent of x over 1 minus tangent of x. I want you to verify that equals tangent of pi fourths plus x. Right? So this is the same thing we did in 7.1. My same hints apply. Start with the more complicated side. You see a trig function being squared. You think of Pythagorean identities. When you're stuck, sines and cosines, all that fun stuff. Now, in the hierarchy of, quote, complicatedness, I would say that if your argument, that's the stuff inside the trig function, if your argument is not a plain old simple x, theta, y, whatever variable you use, that would be, quote, more complicated. So in this case here, I'm actually going to start on the right-hand side. Even though the left-hand side is a fraction and most people are afraid of fractions, the fact that this angle is not a simple x would mean to me it is, quote, harder, so I would start there. Well, look at what we have. We have a tangent of a sum. Fortunately, this lesson, we can handle that. If there's a plus sign inside of a tangent, we have a formula to take care of it. So all I'm going to do is just follow this. So I'm not making it up. I'm not like, it's not magic. I'm just following the pattern. I'm following the rules. So in this instance here, in this example, pi fourths will be alpha, the first angle, and then x will be the second angle, will be beta. So let's go ahead and do this. According to the pattern, it's going to be tangent of the first angle plus tangent of the second angle all over 1 minus tangent of the first angle, tangent of the second angle. Now, fortunately, these guys here, since I put an actual angle instead of a tangent, it's not a variable, we can figure it out. And I hope everyone knows that pi fourths, tangent of pi fourths, is 1. And lo and behold, that's exactly the left-hand side. That's exactly what we wanted, right? So That was sort of like a wimpy example, but I mean that's basically the idea. I'm not really changing the logic, except I'm giving you more tools, um, more identities to use when you're proving these statements. So the moral of the story is 7.2 is going to be very similar to 7.1. The only difference is if you ever see sines, cosines, and tangents taking of a sum of an angles or a difference of an angles, you just have new formulas to follow. So I hope you can go ahead and dive right on in, practice these verification problems, practice these evaluation problems, and as always, the only way you can get better at this is if you practice. Good luck.